Okay, I think I'll start. Um, so this is where we were the last time. That's day before yesterday. We were talking about the various data pre-processing steps, um, sampling the data, meaning choosing a subset for input into the AI algorithm, then cleaning it, the process of transformation, which we discussed in some detail, and then the process of annotation or ground truthing or labeling the data. Right? Remember, these three terms are sort of interchangeable: annotation, ground truth, and labels. So today we're going to start with a discussion of training data. Again, as I've said the last time, most of this, the actual work of creating training data, using the training data, and so on, is the purview of the AI/ML team, AI/ML scientists. But all of us should know what is training data, where is it used, etc. Right? So, so training data, I think by now most of us understand this. Training data is data that is used for the AI model to learn a mapping or the correlation. So now I'm using the term mapping interchangeably with correlation. Again, I'm doing this on purpose because you'll encounter these various, these different terminologies in real life. So, so I hope it's clear what this means. You're mapping between features or covariates and the outcomes or the labels. And training data is the data used for the AI model to learn this mapping. Right? And in order to provide the label or to create training data for the AI, you require an annotation process, as we've discussed before. Right? So, for example, in our LFU project, the training data consists of the patient-related information or patient-related covariates as features, and the outcome of TB treatment, which could be LFU, as a label. The AI is trying to predict the label from the features. Right? In our Anthro project, the features are the baby video, the label is the baby weight. Together, these constitute training data because the AI has to learn from this how to map features to label. Similarly, in our Cotton project, the parts of the image are the features, whereas the actual count of pests is the label. And again, when you supply training data to the AI algorithm, you have to give both features and label. Right? So much of this is repetition. As I've said before, collection and processing of training data is an internal exercise. It's an exercise that the AI/ML team does, and it involves an algorithm or a piece of code that is run on the training data. Right? The output of this exercise, so when you finish running this code, which is also called training the AI algorithm, the output of the training process, the output of this exercise is an AI model, which is a software file containing values of various parameters of the model and the instructions for applying these parameters to new data. Right? This is what an AI model is. Right? And when you apply these parameters to new data, you're predicting a label on the new data. This is essentially saying in words what we saw in the picture the last time. So it's the left part of this picture. Right? You provide label and features. Together, they constitute training data to an AI algorithm. There's a training process that happens. Output of the training process is the AI model. AI model can take in new features and predict a label for them. Right? That's the purpose of the AI model. So I'm just saying the same thing here in words. Now, what's important for us to understand is that typically an AI model, again, there are some exceptions to this. I'm not going to get into exceptions here. But typically an AI model, we often call this a supervised AI model, cannot be developed without training data. Right? You need training data because it has to learn this mapping from features to label. Right? On the other hand, inference data is the data on which the AI model makes a prediction. Inference data doesn't come with a label because then that destroys the point of the AI. Right? The point of the AI is to actually predict a label on the inference data. Is that clear to everyone? Any confusion there? Inference data is the data that the model will actually operate on in practice and predict a label for it because it has learned these correlations or mappings from the training data. Yeah. So the performance of a model in terms of accuracy or any other metric is very sensitive in different ways to the training data that is supplied to it, but it is also sensitive to the inference data. And let me explain. So if you supply the AI algorithm with a different set of training data, meaning a different set of features and labels, it's going to learn this correlation or mapping in a different way. And so you get a different type of model, not a different type of model, but a different model, meaning a different set of parameters at the end of the process of training. Now, this new set of parameters may have a very different performance from the old set of parameters. So in that way, the performance of the model is sensitive to the training data that is supplied to it. It is also sensitive to the inference data because the inference data is the data on which you evaluate the model performance. So a model may perform very well on one data set, one inference data set, but may perform very poorly on a different inference data set. This is why we keep saying you never know how well AI model is going to do until you put it in deployment. You can do all the internal testing, but when you actually deploy it, it will encounter a very different set of inference data and therefore produce different results. Right? So is this clear? Any questions? Yes. Yes, Prashant.
Hi, Alban. Can inference data be used later to train the model to improve the efficacy of the algorithm or to better train the model in the future?
Yes, yes. So if the inference data is manually labeled later, see, you need labels to train the model. You can't use the predicted labels of the AI to train the model because that defeats the purpose. The AI prediction could be wrong, right? Yeah. So you need to manually label the inference data, and then you can use it for training a future version of the model. In fact, that's exactly what you should do when you deploy an AI model. You have one set of training data. Let's call that set 1, right? Using set 1, you create model 1. Model 1 is then used in the field and it does inference in the field. Some of that inference data can be labeled and included in the training data set, and then you create model 2. Model 2, again, you use in the field, do inference on new data. Again, some of the new inference data can be labeled again, integrated with the old data to create a larger training data set, and you train model 3, and so on. So in this way, you have to keep, this is the way you keep revising your models. And you're always keeping up with current data in that way. Question?
Alban, Malay is asking, if a model is trained on daylight video of a newborn training data, it may not work well on nighttime video inference data, right?
Very good. Yes, correct. Absolutely correct. Is there a follow-up question, or that was the question?
Aishi has one more question.
Sorry?
Aishi, go ahead.
She got dropped out from the call.
Okay. Alban, is it fair to say that in our space, where your initial data has so much of uncertainty and noise, and so the initial model performance will be of a nature it is always good for us to think through in the design of systems that even if we get into inference, to have a period of time where the inference is supported by labeling as a feedback mechanism until we reassure ourselves as scientists and others that we have seen sufficient data for us to then give a thumbs up with respect to the quality of the model. Is that a better way of approaching, in general, our problem?
Yes, in general, that is the best way of doing it. Is actually to what's called a passive deployment, where you are just using the AI model. You don't act upon the output of the AI model, but instead you have a labeling process going on to both test how well your previous version of the AI model did, as well as to create new training data. And this can happen, this can be necessary for a number of reasons. One is, Shekhar, the reasons that you described, that your initial data was noisy, not very diverse, etc., etc. But it could also simply be that we didn't have enough initial data to train a good model. Remember, AI is data hungry, right? The more data, just as a thumb rule, the more data you give it, the better it is.
And also, Alban, is it also another thing that as program people, as systems analysts, and as just individuals who don't write algorithms, but who want to understand the space well, whenever we find that the human-based intuitive characteristics of a population changes, if we feel, for instance, and it's just an example, it is not, there's no proof that I'm just using it only as a maybe an inaccurate example also. If we go from one demography to another for baby weight, and if we believe in some measure that there is going to be a change in the basic demographic of the baby weight, then the earlier model, which was trained in an earlier demographic, will tend to naturally fail in the new demographic all the time, correct?
Totally. That's, you should expect that. I mean, we know, for example, that European babies and African babies look different from Indian babies. If you have a model that is trained on Indian babies, you would not expect it to do well out of the box in Europe or Africa.
So then you have choices to make.
Yeah, you would need to collect data from that demography.
Correct.
And one way to do it is to actually deploy it, test the model, and you kill two birds with one stone. So you test your Indian model. Let's say you take it to Africa. Right? In deployment, you can test it. You can test its accuracy in Africa. At the same time, if you know the true weights, you've created new label data that is relevant to that demography. And you can use that label data to retrain the AI.
And in a real life setting, because this conversation has happened, so if we do cough testing, for instance, in India, and there's a desire, USAID is already expressed, we're not yet ready for it, to be able to roll this solution out maybe in Africa. Maybe the inherent voice characteristics of individuals from that demographic will be different. And so we need to either retrain the model or do something totally different, isn't it?
Yeah, that's right.
So the takeaway for all of us is, as we enter new geographies where we a priori know or beforehand know maybe something is different, greater caution must be exercised rather than being sure that this will work well. More important, the fact that it doesn't work well in new areas is a proof to a certain extent that it was trained on a different data. So for us practitioners, this is very important to keep back of our mind.
Yes.
JK has a question. Alban, is inference data synonymous to testing data?
Not really. It can be, but inference data is just the data on which you use the AI. Now, part of that inference data can be used for testing the AI, and then you will have to label in order to actually test how well the model is working. But most of the inference data may not be used, may not be labeled at all, but you're still doing inference on it, meaning you're predicting something. The AI is predicting something.
And a related question is, how is validation data different from testing data? There
I'll
is
come to that. I will come
training, validation, testing
Yeah, yeah, yeah.
partition.
I'm coming to that.
Malay asks, similarly, if we have a reason to believe that Nikshay data quality has changed due to significant change in training, supervision, etc., model may require to change too, right?
Correct. Absolutely correct. We should evaluate the model. We should expect that the model will not perform as well as it is performed in internal tests. So we should be prepared for that. But we should certainly evaluate it on the changed data. And then if we find, as per expectations, that the model does not perform well, then we need to retrain it on the new data. Again, I'm speaking a little loosely. I'm saying retraining the model, whereas actually you're retraining the AI and creating a new model.
Alpan, this is JK. Just an add-on question. If we increase or enrich the quality of the data for the next rounds of model, can we expect an increase in the model performance, or it can go in either direction?
So it depends on what was happening earlier, right? So if earlier, because of bad data, the AI found a spurious correlation. Remember, we discussed spurious correlations in the first session itself, that sometimes the AI can just find spurious correlations if they exist in the data. So suppose because the data was bad, the AI was actually exploiting some spurious correlation between the features and the labels. Then when you clean up the data and supply it to the AI, that spurious correlation goes away, and then the AI model performance can degrade. But if the AI is actually uncovering a real correlation, then better data should improve the AI.
That's helpful, Alpan. Thank you.
So if the AI is really doing the thing that it's supposed to do, then better data should improve it.
And JK, I think here is where, although this is not a mature field, explainability helps determine the two causes that Alpan said. Is it spurious or is it real?
Yeah.
Right, Shekhar.
I have one question.
Yes, Malay.
So let's say for LFU solution, we have trained the data, we have trained the model using Nikshay data for 3 years.
Correct.
Now we have reason to believe that from 4th year onwards, there is a significant shift, which is, let's say, sort of permanent.
Mm-hmm.
In that case, do we need to ask the model to, or do we need to train the model only on the data from 4th year onwards? Because the previous data may make some noise.
Correct. Yes, only if you know this shift is going to be permanent. If it's transient, then you may use a mix.
Right.
But if you know the shift is going to be permanent, then it's best to
Agree.
train it on the new data.
I mean, anyhow, it's a theoretical question just to understand the concept.
Yeah.
Okay.
No,
Got it.
yeah.
Thanks.
And Malay, the idea that Alpan is saying is as close as you can get the training data to be the prospective reality. So if there is a change that is permanent, that you believe is also part of the data collection exercise in an operational manner in the real world, or is it just an aberration? So those things have to be understood.
Yeah, and in fact, we'll discuss it a bit more. This whole process is called data drift, and we'll come to that.
Mihir, as a perspective, he suggests interesting point about spurious correlations. Given enough hypothesis and enough data will usually show that at least one of those hypotheses is true up to statistic significance. This means we need to be careful in choosing hypothesis, using domain knowledge, etc., rather than just looking at data. So that's a mouthful. So either Mihir or Alpan can explain.
Yeah, Mihir, you want to take a crack at that?
Sure. So I guess the point was that if you have enough data and you propose many hypotheses, you might say that, maybe you might suggest that, so in the LFU example, maybe you say that patient age is correlated with patient weight, age is correlated with location, etc. You generate thousands of hypotheses. Usually the data will show that at least one of the hypotheses, like you get at least one spurious correlation that will show that two of those columns are actually strongly correlated. And this might not be because of anything on the ground. It just might be an artifact of the data. So rather than just looking at the data and coming up with ideas to do the modeling, it makes more sense to carefully have domain knowledge and try and analyze what outcome might be predicted by what variables, and sort of come at it from the domain knowledge angle rather than coming at purely from the data angle. Yeah, that was the point.
Yes,
hope-
so the
yeah.
problem definition itself should come from domain knowledge. I mean, you don't look at the data set and say, what can I predict from what using this data? That would be a wrong approach.
And Alpan, wait, I think what you said is super important. This is the common question that all of us will get. It is a guaranteed common question. Here is what people will do. They will say, ये data हमारे पास है, बताओ इससे क्या निकाल सकते हो?
Yes.
Guaranteed. It is the wrong way of approaching the problem, but you cannot tell it to the counterparty. You cannot tell them it is wrong. So you have to be intelligent and weave through and come to a domain-centric agreement with the counterparty. Maybe there's a doctor, or maybe there is a XYZ specialist at their end, who may have an hypothesis can be equivalently called just a theory. अपने मन में कुछ एक मनगढ़ंत कहानी हमें लगता है ये चलेगा. Domain को मालूम है. जैसे Dr. Neeraj will say when a person coughs to a certain extent, he can make out if a person has TB or not. So he's trained his mind. So equivalently, a lot of domain experts have intuitions. They have a sense as to what's going on in their domain. They generally, through hundreds of thousands of observations, they will know generally ये उसके साथ ही होता है, ये इसके साथ ही होता है. Medical में बहुत ऐसे correlations है, and generally बहुत रहते हैं. But over and above that, there will be other factors also. And so what Mihir, I think, is suggesting, and Alpan is also saying to all of us, is that don't ignore these intuitions. Don't cast them aside in favor of just looking at data in a mathematical manner. Data in a mathematical manner only makes sense in the context of the underlying body of knowledge that describes a domain, whether it is agriculture or rural matters or water sanitation or health or TB. You cannot ignore the domain. And it is the domain that gets encodified or codified into data. So the domain individuals have to have a decent understanding of the way that encoding happens, because that encoding means converting it to code. Male is M, female is F, tall is T, short is S. Something like that keeps happening. Super important for you to create that connection. If one of these two connections breaks, either the mathematical work that the AI guys do or the domain intuitions that people have, it impacts the model. I think that is what they're trying to say. Neha had a question.
I think I heard it in the class, and I read it somewhere that when AI does correlations, sometimes they cannot be explained. So so because you are talking about using domain knowledge to evaluate whether those outcomes, the correlations are right or not. I just wanted to understand if you can't actually logically explain what AI has done, then how does an individual or expert actually will evaluate those correlations? If, for example, there isn't any data that exists on the ground for that correlation to be justified.
Right. So yeah, explainability is generally difficult with AI. There are ways to do it, but they're not always consistent with each other. But evaluation is a different process. So you don't evaluate the correlation, you just evaluate the output. So you ask, how good is my AI at predicting something across different cohorts? And if it is fairly robust at predicting for different cohorts, then it's useful. At some level, you don't care what the explanation is. You can think of it as a black box that you provide features as input, and it predicts a label. And you have to evaluate this black box without knowing what's going on inside it. You can just evaluate, just like you evaluate everything else. medical devices that you use, you don't know how they operate. You don't need to know how they operate. You don't need to know how a stethoscope operates inside in order to evaluate how good it is. Right? You can externally evaluate. My stethoscope is telling me this person is having abnormal heart, heart rate or something like that. And you can independently measure whether the person really has an abnormal heart rate.
Okay,
Like
understood.
that, you don't need to know what is going on inside the stethoscope. Right? So it's similar thing. Yeah.
Alpan, only one other thing. Neha, your question is actually an exceptionally good one, and I'll tell you why. There is a natural curiosity that we have to try and understand things. And if we don't, then we get all confused, we get stressed out. So you really need to then get into the what we call types of problems. Let us say you have 15 data features, something, height, this, that, and then you're predicting an outcome. There, the human requirement to unravel what is going on tends to be very heightened. It's also natural and correct. There is also a benefit to it, because what AI can do is uncover a correlation which a human being has not seen. And that particular correlation may be very powerful with respect to lots of things. So that aspect is always, and to a certain extent in my observation, Alpan will correct me, there is a greater probability that even AI will be able to explain that. So that is one type of problem. But when you look at an image or a video which has not 15 features, but 15 million features, because every dot is a feature. When you have 15 million features, then there is no chance that you can get to it. It just does what it does, and you have to be ready for it. So it's a nuanced question. It's not got a clean answer. That's all. Alpan, you can add.
Yes. I mean, the way an AI model takes a decision, just taking Shekhar's example on an image, is very different from the way a human does. And we discussed it last time, right? You have these so-called adversarial examples where you can make small changes to an image that are not discernible to the human eye, and that will completely throw the AI model off. So obviously, it's looking at things in a different way than a human does, and very hard to interpret how it's looking at it. I mean, there are methods. It's not like there are no methods to interpret, but all methods don't necessarily yield the same answer. It's not very reliable.
I was thinking of this teleradiology example
And
where the
Nilam,
X-rays-
I think
Sorry?
Sanjit को आपने बैंगलोर से मुंबई बुक किया है ना?
I'm
अयो
sorry.
वो मुंबई से बैंगलोर था. अयो
I'm so-
हमने भी देखा नहीं.
Sorry, आपकी वॉइस ब्रेक हो रही है.
हाँ, हम सब लोग दोनों पढ़ रहे हैं मुंबई टू बैंगलोर, मुंबई टू बैंगलोर. पागल है हम लोग. हो सकता है क्या?
Talking to somebody, not on mute.
Okay.
नहीं कल है. तो आप
Okay, go ahead, Neha.
I was
हाँ हाँ हाँ.
Shekhar,
मैं ओके वेरी गुड थैंक्स. किसी ने देख लिया.
She made a mistake.
She sent it to us. Both of us have read it ulta. She sent all the information to us.
You didn't tell her Mumbai.
You need to get up. I don't think he heard.
Alpan, maybe you will have muting rights.
बोलिए.
Oh.
Okay, let me see. I don't have muting rights.
Okay.
नहीं बॉम्बे टू बैंगलोर चाहिए.
I know. Okay, let me just ping Shekhar 1 second.
Oh, sorry.
He heard that. Alpan, he heard that. He muted himself.
Okay.
I pinged him.
Okay.
Okay. Thank you, Sonu.
Okay.
Sorry. I was just thinking from the perspective of the teleradiology example, Alpan, where these 14 points are tracked And there was this whole
14
conversation.
features, not
14
points.
features, sorry. These
Yeah.
14 features are tracked, and there was this whole conversation about bias and how teleologists understand and all of that. And I was from like the thing that Shekhar said about processing the information and making sense of it. So I was trying to understand how much of it can be explained to the person using it, and make sense of that information versus you at certain points you say that, hey, these feature correlations cannot really be explained. So where does the teleradiologist apply their mind, or like they say, okay, this is what AI thinks, how do I evaluate it, for example, right?
No, so you're asking many questions within
At the
that
same
one
time.
question. So one is explaining to the teleradiologist why AI is doing what it is may be difficult. I mean, again, there are methods. There are ways to, I don't want to go into technical details, but there are ways that you can highlight parts of an image that the AI is actually looking at to make a certain decision. So you can do that and supply that information to the teleradiologist that, when the AI came up with this decision, this is what it was looking at. You can do that. But more importantly, what the teleradiologist needs is just to know what is the decision that the AI took and if it is correct or not, using his own or her own expertise.
So if I could just jump in,
Yeah.
I think Alpan over here, I think Neha's perspective is that we often, when we are designing interfaces, we struggle with saying how do we build trust, because trust is built over time,
Yes.
and there's some initial friction that you can always expect, and
Yes.
that's the phase which we need to build a bit of explainability
Yes.
into it. Now, and right. So
Right.
I mean, one of the conversations that the design team had, we were looking at other examples, and we always said that sometimes the explanation won't come from the model itself because
Yeah.
it's a black box, but we'll
Yeah.
have to use other indicators to kind of, maybe give some reference explanation. Neha, I mean, just some context that I'm building over there. But Arpan, do you have any other suggestions for us on how?
This is a problem with AI solutions in general as compared to other technologies. So it's not something that's going to go away. It is difficult to establish trust. And one way is, of course, over time, if it keeps making the right calls, if the accuracy is high in various situations, then that builds trust. But that's a process that happens over time. You can also, in computer vision type AI, where you're processing a photo or a video or something like that, you can do what I said, which is that you can create a visual representation of what part of the image or what part of the video the AI is actually looking at in leading to the decision. Over time, the user might stop evaluating and relying on their wisdom. Yes, so that means they've lost trust in the AI if they've stopped using the AI and relying.
No. What I meant was that once you build the trust over a period of time, you're like, okay, AI is giving me mostly accurate responses, so I can, trust the kind of suggestions that are being made. So
Yeah.
then, once the user has built that kind of trust, do they they would usually stop relying on their own wisdom instead, because we are discussing.
Yeah, so it depends on what you're using the AI for, right? If you built an AI solution which was a replacement to the user's wisdom, we usually don't get into problems like that, right? We get into problems where the user genuinely finds it difficult to do it without the aid of something. I mean, for example, counting pests on a trap may be genuinely difficult for the user to do. It's not like they were using their wisdom earlier, right?
Understood. I have a lot to think about. Thank you, Alpan, for that.
So we typically don't want to get into situations where we are replacing the user's wisdom. If the user is wise enough to know what to do, we don't even want to get into that space and use AI. Right?
Okay, Alpan.
Okay, let me go to the next slide. Yeah. Oh, sorry. Yes, go ahead, Sun.
Yes, sir. Good afternoon, sir. Sir, suppose we are about to get some data from any institute or for any specific use case from some organization or some institution, what should be the characteristics of that data? Like, if we are anticipating that clear-cut data will come with labels and annotations, that wouldn't be a problem. But what should be the characteristics of data which we should be asking for?
So in general, the ideal situation is that you want a large amount of high quality labeled data. And I will talk about this in a minute. So the quality is important, the quantity is important, and the quality applies to both the features and the labels. I mean, in a nutshell, that's what it is. And it should be in a consistent format. You don't want, this is part of quality, right? For example, you don't want the date column in which part of the dates have day first and month, then second is month, and then in part the month is first and the next is day. This is one example. Right, so consistent form.
Suppose, yeah.
Accurate, high quality, complete, both for labels as well as features. We'll discuss this.
Just one more clarification, sir. Suppose we talk about fundoscopy solution or teleradiology solution related to chest, there are 8 to 10 such things which we can see on that particular thing. And so do we need to go with the specific single use case per data, or we can get some mixed sort of data also? What we should stress more for?
No, I don't understand your question.
Suppose there are, there are 10 diseases in chest which we can see through X-ray, or there are some 10 diseases in posterior chamber of eye where we can see those 10 diseases.
Yes.
But there may be some pictures which is clear cut going towards one specific diagnosis. But there may be pictures which may not be very clear to ascertain the diagnosis. So I just need to ask which kind of data we should stress more for. A clear cut one, or the mixed kind of one, or both, or if suppose both, what should be the ratio?
So so generally, so it's complicated. I'll explain this in a minute. It's somewhat complicated because you do want a situation where you want the data to be clean, but you don't want it to be unrealistic. Right? This is the balance. So you can't have a situation where the data is so clean that it simply, the AI that is learned on it is unusable in the real world. Right? So you want data to mimic the characteristics of the real world. But at the same time, it doesn't make sense to completely train on very dirty data. There is a judgment call here, which sort of varies case by case. I mean, it's difficult to make a general statement here.
Okay.
But we'll talk about data quality in a minute. Okay. Now, when you interact with the AIML team, you may often hear about this concept of data splits. And this is also a question that was asked a couple of minutes ago. There is as part of the internal AI model training or development process, the training data that people use. So the set of data with labels, what I mean by training data is features with labels, is often split into 3 parts. There is what's called a training set, which is what the algorithm is trained on, then a validation set and a test set. So splitting the data in these three buckets. So let's say you have 100 labeled data points. You may decide to put 60 of them in training data, 20 of them in the training set, 20 of them in the validation set, and 20 of them in the test set. So splitting the data in that way is called a data split. Now, what is this data split? Why is it necessary? So first, the training set is the data that is used to train the model, right? So that is clear. It is the data that is used to learn these correlations or mappings between features and labels. Now, I'll come to the validation set in a minute. The test set is the data that is at the end used to evaluate the model in our internal evaluations. Okay. So typically the AI algorithm should not see the test set at all until it is actually to be evaluated. The validation set, on the other hand, is something in between. Now, there are various parameters in the model. So for example, I'll just give you a very simple example. Let's say you have a deep neural network AI model. You don't need to know what a deep neural network is. All you need to know is that it has to be trained for a certain time, right? So it has to be able to process the training set over a certain time duration. Now, how much time do you need to train it for? Do you need to train it for an hour? Do you need to train it? Again, I'm using time in a somewhat loose sense. It's really internal cycles that we call epochs. But for the sake of this explanation, let's call it time. The question then is, how long do you have to train it for? This length of time that you have to train it for is called a hyperparameter. Okay. And the validation set is used to find the best value of the hyperparameter. Meaning, you train the model of the training set. Let's say you decide that I'm going to train my model either for 1 hour or 3 hours or 1 day or 2 days. So you pick these 4 different training times. So now what do? You have the same training set. You train the model for 1 hour. Then you ask, how accurate is the model on the validation set? So you compute its accuracy. Then you take the next time, which is 3 hours, right? So you take the same training set, train the model for 3 hours. That results in a different model with a different accuracy. Again, you use the validation set to compute its accuracy. You do this for all 4 values of this time hyperparameter, and you find which gives you the highest accuracy. So this process is called optimizing the model on the validation set. So at the end of this process, you've decided, let's say you find that training it for 1 day is the best thing. If you train it for 1 hour, 3 hours, or 3 days, you really get lower accuracy on the validation set than training it for 1 day. So I'm going to fix that parameter and say, I'm always going to train this model for 1 day. So the validation set helps you do that. The test set, on the other hand, is completely untouched. It is something that is only used to evaluate the model at the end, after you've decided all the hyperparameters. Okay. Now, there's different ways of doing the split. Sometimes, you split the data, the training data randomly into these 3 buckets, right? Sometimes you do it in a longitudinal manner, meaning with time. So you might say, let's say you have data from dates January 1 to June 30, and you can decide that January to May data I will use in the training set, May to month of May data I can use in the validation set, and month of June data I use in the test set. That would make sense if you have, if you expect the data to change over time, and you will always have data in the past to train the model, and you'll be evaluating it in the future. So longitudinal split often makes sense in a real world deployment context. But you'll see that in most research papers, the split is done in a random manner. For our work, in most cases, it makes sense to do these longitudinal splits. There are other ways also of doing these splits. depending on how you want to evaluate the model.
Can
So-
you explain again why longitudinal manner is preferred in our work?
Because that is how the model will be used in deployment, right? When you actually deploy the model, it has been trained on past data always, but it is being used on future data. So you want to mimic that process in the lab. So you split it longitudinally. You train it on past data, and your test set is the future.
So I guess, I mean, every or almost all the AI ML model work that way, right?
Yeah, applied AI usually the best way to evaluate it is using a longitudinal split.
Okay. And second question is, can you explain again about, so I could understand about this validation set, why we have it and what is the purpose.
Yeah.
I just could not understand clearly about this hyperparameter word or, matlab, can you explain it again?
So hyperparameter, so okay, it's slightly complicated. So as I've mentioned before, an AI model consists of various parameters. So again, if you think of a regression model, the slope of the regression line and the intercept of the regression line are the parameters. In the process of training, these parameters keep getting updated.
Right.
Until you reach some optimal value.
Right.
Right. Hyperparameters are not parameters that get updated in the process of training. So hyperparameter can be, again, in the regression example, do you want to, is it better to fit a line or a quadratic curve or a cubic curve? If this is the decision, then that's a hyperparameter. Line versus quadratic versus cubic. So then you need to evaluate each of these separately on a validation set and ask which one gives me the highest accuracy. Is a linear fit more accurate? Is a quadratic fit more accurate? Is a cubic fit more accurate? So that is an example of a hyperparameter, deciding on the order of the curve that you are going to fit. The order is a hyperparameter. Does it clarify things or no?
Unfortunately, no. How are we going to like deal with this word hyperparameter?
You are not.
Or less common.
Completely internal. So you don't need to worry about. You are not going to deal with it ever.
Perfect.
It is part of the process of training a model.
Is it part of training or validation?
It's actually, well, it's actually part of the process of training a model. The eventual validation is always done with a fixed set of hyperparameters and a fixed set of parameters, and you evaluate the model on the test.
Okay. Over.
Yes, JK.
Alban, I was just curious, what is the disadvantage of not having a validation set in a experiment? Is this a mandatory partition or is this a desirable partition?
Any AI model that has hyperparameters, you should ideally have a validation set. I mean, some people use shortcuts of not having a validation set, but it is bad practice typically not to have one. What they do is they just try to find the hyperparameter that fits the test set well. But then that is cheating because then you're not doing a true evaluation of the test set. It's not a blind evaluation. So it's always good practice to have a validation set. But
so is there a recommended size for the partitions?
No, there are some theorems on that, but this whole area is fairly loose. I mean, this is empirical. There's no typically, the training set, because you're using the training set to find the correlations, you want the training set to be as large as possible. On the other hand, the validation set and test set also should not be so small that your accuracy is not statistically relevant.
Understood.
So you play this game of making the training set as large as possible and yet making sure that training and test are reasonably sized. And again, this is completely part of the practice of the AIML team. You guys don't need to worry about this at all. I'm just talking about this in order to introduce terminology that you may encounter when you.
Sure, Alpan. We are seeing through that lens only. I was trying to draw some opinions or reflections on the prevalence of a particular event of interest and the volume of data at hand. Example, you have two scenarios.
We'll talk about volume of data later. We'll come
Sorry.
to
Okay, fine.
So, once we are satisfied that the AI model has done well on the test set, so this is after you fix the hyperparameters and everything, then you deploy. You typically deploy the AI model, meaning you start using it in the real world. And at that point, at the point of deployment, there is really no more training or learning. That will happen post-deployment, after it acts for some time upon data and so on. But at that point, your training and learning is finished. You've evaluated on the test set and you've deployed it. And deployment means that the model is exposed to real data, which is inference data, and it makes label predictions on that data. Is this clear? Okay. So now we come to data quality. I know, Mihir, can you speak? I can't see what you're commenting.
No, I was just comment trying to give some context to the discussion about it. Wasn't a question.
Okay. So we talked a bit about data quality earlier. So what is data quality? It means having accurate and complete features and having accurate and complete labels. It's as simple as that, right? You don't want missing features, you don't want missing labels, because then it becomes more difficult for the AI to learn this correlation or mapping. So if the AI ends up learning the wrong mapping or learning a random mapping, then the model will not work well in practice. So on the right, you can see two cartoons where in the first case, you have high quality data, and the AI has learned some mathematical function that it maps to predict the label from the feature, right? And I'm calling that function f. But in the bottom figure, let's say you have features that are noisy or corrupted in some way, and labels that are also noisy. Now, what will the AI do? It will learn to find correlations between noisy features and noisy labels. So it will find all the wrong correlations. And that model will typically not work well in practice. Right? So you don't want data that is too noisy. Right? In practice, there's a sort of judgment call. As I've said earlier, I'll give you a concrete example. In the CUF project, many of you have been associated with that project. The question was, during data collection, how isolated we want to keep the individual. Right? Now, there's two extremes to this. One is you keep the individual completely isolated in a soundproof room. So you get very high quality data, right? There's no other external noise, nothing. But that's not what we did. And why is that?
We wanted to mimic the real life scenario.
Soundproof rooms. Suppose it was feasible for the data collection.
I mean, performance wouldn't really indicate what the real world scenario would be. So
the performance would not indicate the real world scenario, correct? But
and you also wouldn't be able to. I mean, you would need complete data ultimately to train it on noise.
Yeah, it would not work in the real world because the real world is noisy. You can't. If the aim of the model was only to be used in a soundproof room, then it's fine to do that kind of data collection. But we expect this model to work in a community setting, which is not a soundproof setting, right? So that's why we didn't collect the data in a soundproof setting. So we actually degraded the quality a little bit in order to mimic the real world deployment scenario. Now let's talk about the other extreme. Why did we collect the data in a railway station where there's all kinds of sounds? Anybody? This is very intuitive, by the way. It's not that complicated.
Signal is diluted.
Sorry?
Signal is diluted.
signal is diluted. It will not be able to learn any correlation because all the audio that is picked up is the noise of the trains, not the noise of the car. Right. So you have to typically make a judgment call on this. Right? You want the data to be slightly noisy in order to mimic your real world deployment scenario. And that's why there is so much experimentation in AI. Right? Should we, that's why it's so important also to have consistent data protocols between data collection for training the model and the usage of the AI. You want those two protocols to be exactly the same. Otherwise, the AI is going to encounter a different type of data than what it encountered during training. Right. So I have, JK, I'll just get to your question in a minute. I'll just get to the last point here. So the last point is somewhat nuanced. If the deployment environment contains data of poor quality, should the model also not be trained on poor quality data? It's partly true. The general answer is no. The data can't be of really poor quality because you lose signal. Right? Poor quality data typically contains a lot of random errors, and a model trained on data with random errors will run a random correlation or random mapping, and it won't perform better on poor quality data. On the other hand, you do want to have a slight amount of noise or error in the data, and make sure that in the real world situation, the way you use the AI is such that you can work with that slight amount of data. So you don't want to completely overwhelm the signal, but you want to make sure that you can operate the AI in a real world situation. Right, so that's the balance. Yes, JK.
Alpan, I wanted to check with you. Currently, as per the data collection protocol, we are driving the message of 3 feet distance between the source of the cough sound and the receiving mobile phone. Okay. So we are having an assumption that futuristically, community health workers might be able to use the tool. But with this kind of a training data set, is it possible futuristically in a scenario where the patient himself is using his own personal phone at a much lesser proximity? So the 3 feet barrier is broken. It is much closer proximal. Will the model still work? Because common sense says that the distance between the source and the receiver has decreased, so it must have picked up a stronger signal. Can this assumption be true?
Yeah, it's picked up a stronger signal, so ordinarily it should be okay. You can also, if it's just, if the distance is just controlling the strength of the signal, you can also weaken the signal slightly in software if that works better for the AI. So that is, those are experiments you can do in software.
But it has a conflict, no, Alpan. Our models were not trained on the taking the distance parameter, right? It was standardized.
Yeah, but that's where you have, again, this is where the AI team have to sort of think about this a little bit. What will be the effect of decreasing distance? See, there are various ways in which the so again, let me step back. Overall, in deployment, the deployment scenario should mimic as far as possible the scenario in which training data was collected, right? So that much is clear. Now, what happens if it can't perfectly mimic the data collection scenario? What happens if the deployment scenario can't perfectly mimic the data collection scenario? Then the question, then it becomes more nuanced. Well, it may not perfectly mimic the data collection scenario in different ways. So what are those different ways? One way is, JK, what you mentioned. Suppose the person is actually closer to the phone. Closer to the phone is a solvable problem because worst case, you can just decrease the volume of the signal. And otherwise, it should look exactly the same. And so the AI should be able to handle it. Now, let's take a second scenario. Suppose the patient is actually going to be far away from the phone, like 20 feet away. Would you expect the AI to work then?
Unlikely.
Unlikely, because maybe the relevant part of the signal has just gotten lost. and you can never recover it. Third scenario, suppose the patient is still 3 feet away, but is traveling in a bus. Again, unlikely, because that you're introducing all kinds of extraneous noise that the AI doesn't know how to process. So this is where it's the job of the machine learning scientists to inform the program team that these are the scenarios we should be able to handle in deployment. These are the departures from data collection scenarios that we should be able to handle in deployment. These are the departures that we probably will not be able to handle in deployment. And based on that, a protocol has to be developed for using the tool.
Understood, Alban. Thank you.
Okay, so now this is a question that everybody has been asking, and everybody asks us as well. How much data do you need for this AI? And this is, actually, this is one of the hardest questions to answer. It's really a hard question to answer because AI is such an empirical field at this point. It's very difficult to tell. It's not like statistical methods where you have sample size formulae in order to achieve a certain significance level. There are no formulae like that for AI models because they are highly nonlinear models, right? So the standard answer you will always get, and I know it's the most frustrating answer, but it's the standard answer you'll get from AI/ML scientists is the more data you have, the better it is. Because they don't know. They actually don't know. And they know through practice that the more data you can feed the algorithm, the more the accuracy improves. This is known. Right? So this is what they say. There are some ground rules and simple thumb rules. So one is that if it's going to be a deep learning model on image data, and you're training it from scratch, you typically need, for each class, meaning each value of the label, you need about 1,000 to 2,000 images per class. There's a lot of research going on into decreasing this number. And there's also ways that you can reduce this requirement significantly if the model has already been pre-trained on other images. Right? But this is sort of a thumb rule. If it's a classical machine learning model and not a deep learning model, the classical ML models turn out to be much less data hungry simply because they have fewer parameters. And there, the typical thumb rule is you need about hundreds of rows per class. Should be enough. So, for example, the LFU problem, where I think the best model is a classical model, and you're predicting it's a binary classification problem. You're predicting whether the patient will go LFU or not, right? So one of two classes. So typically you would need a few, in order for this model to do well, say 300-400 rows in the LFU class, 300 or 400 rows in the non-LFU class, and you should start approaching the accuracy that you get with thousands of rows. It won't be quite the same, but you will start approaching similar accuracies. Another general thumb rule is small, high-quality data sets are generally larger than large, low-quality data sets. But sometimes you don't have a choice, right? When we're getting data from partners like Nikshay Data, you can't dictate the quality and tell them that, look, I need data of a certain quality. So when you can't dictate the quality, it's safer to get a lot of data. And this is one of the reasons why we've been able to do reasonably well on the LFU problem is because we got a lot of data, far more than hundreds of rows per class. That's because the data quality is pretty poor, right? Very, very important, data diversity. And that means that you need data from different locations, different time periods, and under different conditions. And you need all the locations, time periods, and well, time periods you won't be able to control, but at least locations and conditions that are relevant to deployment. Right? If you're going to deploy in rural Bihar, even if you don't get data from rural Bihar, you should be able to get data from a region that's similar to it, so that the model actually works well in rural Bihar. Right? And this is so that the AI algorithm can learn to correlate better across a diverse range of conditions. Okay? Now, the time problem is something you can't reproduce. So, if you're going to use the model in 2023, you can't ask for data from 2023. Right? You don't have it because we haven't reached 2023. So for that reason, it's always better to have continuous data collection, not a one-time dump. And often this is taken care of through a deployment and evaluation process. So if you deploy, as you deploy, you actually evaluate and therefore label a subset of the data, then that subset can be used for training a future version of the model. And that subset is always there in the future. And so you take care of the time diversity problem. Okay. And the last point is really a repetition of the small high quality and large low quality, which is that the less accurate the data, typically the more data you will need. Because the algorithm has to learn to average out all the errors in the data.
Can you please explain again what did you mean by class?
Oh, class. So we talked about binary classification versus multi-class classification.
Oh, okay. Classification.
So, for example, in the LFU prediction, you're predicting whether the patient goes LFU or not, right? So that's two classes. On the other hand, if you were to predict all possible outcomes of TB treatment, say there are 7 outcomes, for example, I don't know the actual number, I'm just saying 7, then you have 7 classes.
Okay. Fair enough.
Alpan, does the desired data volume have any relationship with the prevalence of the event?
Yes, it does. And yeah, it does. So if you need a significant amount of data in the minority class in order to be able to model it. So if your prevalence is, let's say you have a binary classification problem, and the prevalence is very, very low, then you need enough data from the low prevalence class.
Understood. But in a real world scenario, if the prevalence of the actual event is say like 5% and the data set that I'm giving you, just to meet your requirements, if I'm matching every event with a non-event, so will a 1:1 ratio be a skewed data to work on?
I'll come to that, JK. I'll come to that. I'll
Okay.
discuss that in a minute. Yeah, you're asking all the future questions right now.
Oh, sorry.
But this is good. This is good. Yeah. Okay, shall I proceed? Let me just pause if there are any other questions. Yeah. Yeah, Neha, go ahead. Then I'll
Yeah.
Yeah.
When you say that AI is currently empirical,
Yeah.
can we say that the examples that have already been worked on, for example, if we are working on the pest detection model, that same model can be applied for other use cases? But you have mentioned that there are like obviously like the variations have to be taken in account. Are there things to be considered beside that when you are using an existing model for a different use case?
Yes. Yes. So if you use an existing model for a different use case, of course you have to first evaluate it as is on the new use case, right? So let's say you have some labeled data for the new use case. Then the first thing you would do is evaluate the existing model. How well does it do? If it does well, then you can go ahead and just use it, right? If it doesn't do well, then you need some training data for the new use case. Now, you may not need as much training data as you originally did in order to develop the AI model, because it's already learned certain correlations. So now with a smaller amount of training data, you may be able to adapt it to the new use case. But again, when I say that it's an empirical science, because I can't tell you how much. It all depends on the original use case, how similar the new use case is to the original use case, what is the quality of the data, what is the type of model I have, it's very variable.
Okay, got it. Akash?
Okay.
Yeah. So my question was like just now, you mentioned like if we are training and let's say we add a new district for inference, so
Yeah.
there should be a similar district available in the training data set. So let's say I am assuming
Yes.
that the measure is something like how good is the government infrastructure, and location is like a sort of proxy to signal that kind of information. For example, let's say.
Right.
So in this scenario, even though I have like a lot of districts which have good governance and bad governance and everything in between,
Yeah.
when a new district comes in, like the model might still need enough data to internally classify itself as a good or like a bad district, right? Like a good governance district or a bad governance district.
Sorry. So
So,
you think the model is trying to classify the district? No.
but internally it might, it probably can build collision, right? So basically,
Internally build a correlation. So if it has seen bad governance districts before, and that bad governance is actually reflected in the features, right? I mean, it will not know automatically. So we are assuming that the features that are supplied to the model actually reflect some of the characteristics of the location, right? So, for example, if I want to, if I have a patient, a TB patient in, say, Jharkhand versus a TB patient in Kerala, right?
Yeah.
There is something about Jharkhand and something about Kerala that contributes to the data we have for that TB patient in Nikshay. That is different. Only if that is true, then all of this, if all patients everywhere look similar, then location is not important. You can train it at one location, apply it in Norway or Timbuktu or wherever.
So no, my question was,
yeah,
like let's say you bring in a new district, right? So if we don't have like sufficient data on the new district, how will the model learn whether it's similar to Jharkhand or Kerala? Like this
based
particular
on the
district.
features of the patients who come from that new district. That's what I'm saying. See, there it will only be able to learn this if there is something about the location that is reflected in the features of the patients.
Understand. Okay.
So there has to be something in the patients. So maybe maybe nutrition levels are lower in Jharkhand than Kerala, and therefore the patients come in with lower weights. Now we have a new district that is similar to Jharkhand in the sense that the patients have lower weights.
Okay.
Then
So
we will learn all those correlations. That I have seen patients like this in Jharkhand, so the prediction should be similar.
understood. So basically, some other features might also convey some information. Like
Yes, there have to be. Otherwise, AI will not know anything about location unless you explicitly encode location. But then it's very dangerous to encode location explicitly, because if you just encode location as a location, it will never have seen that value before, and that may cause other problems for the AI.
understood.
So it's always better to encode characteristics of the location that that reflect in the patients.
Thanks, Vilpan.
Sure. Was there another question?
Alpan, when you say less accurate data, what exactly do you mean?
So, for example, in Nikshay, right, you have patients who are 300 years old, clearly inaccurate. The age is inaccurate.
Okay.
They entered wrong. In your pest management problem, suppose you take a blurry image. Then the boundaries of the pests are inaccurate. Right? Or you take an image of something that's not even a trap.
So less accurate and inaccurate are the same thing here.
Correct.
Okay. Can we also say that training AI model using mildly corrupt data, which is recorded in acceptable diverse scenarios, that's what defines the quality of an AI model? Can we say that? So, for example, you were mentioning that that when we are training an AI model, our data needs to be something which is closer to real life.
Yes.
Data, right? Which means it's not completely sanitized data. It is having some something. I think you get what I'm trying to say here. So
it should be something that that is practical to enforce in real life. Let me put it this way. Yeah.
Okay.
It is not practical to enforce that you put patients in a soundproof room, for example. It is practical to enforce that you keep them away from a railway station or from a noisy market, but instead stay in their home when people are not talking very loudly. That is practical. So then you have to think through this, right? How am I going to use the model? Based on that, you define how you're going to do the data collection.
So you have to think about all the possible scenarios when you are recording that data, right?
No, before. This is what I'm saying. Even before you start recording the data.
Yeah. Before that only, you need to define those conditions, those
scenarios. You have to define the conditions of deployment. Yes. Yes. This is why we put such great emphasis on problem definition. Problem definition includes all of this. Yeah. What is the problem you're trying to solve? How does that translate into an AI problem? How will the solution to the AI problem be used? Where will it be used? Under what conditions? On what population? Everything. Based on all of these things, you define the data collection for the training data for the AI. Now, if you change in between, you say, no, I actually don't want to use this in a home setting. I actually want to use it in a railway station. Then everything goes for a toss. You have to redo your entire data collection.
Yeah.
You have to redo your entire AI model training.
Yeah, makes sense.
Yeah. Right?
Thank you. Thanks, Alpan.
Yeah. Yes.
Alpan, hi. Aditya.
Hi,
is there a way to get almost like a checklist of these things that you just mentioned so that we sort of look out for them as early as possible? So even, let's say, at the time when we're conceptualizing things and writing proposals, for what all we should include?
Well, it's not, this is probably, it is relevant for writing proposals, but I'm always worried about checklists because these checklists will not be exhaustive. You'll always remember something. This is such a case-by-case thing, and that's why I think it's very important, at least in the beginning, for our institute, that when we do problem definition, we have all experts from every area come together to sign off on a problem definition. Once we gain enough experience in this process, we know what kinds of problems we typically will handle over, say, 2-3 years. Then we can distill all this information to create a checklist. But I think at least for an initial phase right now, we will need to have a joint sign-off on the problem definition from all teams, so that we bring all of these aspects to bear. And I think similarly for writing proposals.
Alpan, sorry, Shekhar, sorry for the noise the last time. Suddenly one crisis was precipitated. But a quick comment to Aditya and others. And Alpan, it may be valuable because I see a lot of very important questions in this area.
Yeah.
Aditya and everybody else, the thinking, how will I put it? I'll give you a small example then we'll a lot of times in the pest management example, people will take a white wall and then the inference will say there's a pest in it. So why is this happening? From a human perspective, he will think the AI is just stupid. What is this nonsense? It's a white wall, yeah. Why the hell is it showing a pest in that? But if you understand what Alpan has taught us, you will know that AI had no choice in some sense but to predict some pests there. And why? It was never given training data of white walls. It was never ever told this is a white wall and these are hundreds of white walls and there are no pests in it. Therefore, when the human mind can easily discern this and consider this a failure on the AI model, but as we understand the way Alpan is teaching us how to construct AI systems, the flaw is not the AI model. The flaw is in the usage of the AI system, where we cannot allow it to be used on sundry surfaces. If the whole universe is available as a surface for us, it cannot be, the AI model cannot learn on all surfaces. Now, that's an example I'm using. Now, what is the thinking process when we understand what Alpan has taught us? It is that confine the usage of the AI model to acceptable environmental conditions, usage conditions that are acceptable and solvable by AI. This is the statement. So this is a negotiating statement. It is not a black and white statement.
Yeah.
So AI ML fellows will want to have it slightly more sanitized, but real world may not be. Real world may say, I have to give you data in this manner only. A very good example is CTB. CTB is a ballpoint, just using simple. It may not be totally accurate. Don't worry about that. Somebody puts a ballpoint marker around the hand, but that itself is so flawed and so inaccurate that the AI model will never learn or will find it very difficult to predict properly. The understanding that the domain people and the users and people like us must know is that we must not make any assumptions based on our human understanding of the way AI works. You must not. Even if it is obvious. White paper may, I mean, in a blank sheet of wall, in a blank wall, there are no pests. So why is this AI being stupid and telling pests? That is not the way to think. You should confine your thinking in AI only to, have I given it data for this? And is the data's environmental condition similar to the way it will be used in real life? This is the acid question. I cannot change it dramatically. If I'm showing greenish surfaces or bluish surfaces, then all along I must be thinking of greenish, bluish, etc. surfaces. Suddenly I cannot show it a red surface. I'm using it as an example to emphatically draw the boundary of the way we think. This is a change in thinking, significant change in thinking. You should cast aside your logic of human analysis and confine yourself to AI-based analysis. So I want everybody to ponder over this, because this is the heart of good and bad problem definition. You cannot fall trap to human logic. You only have to understand data, and are the data conditions correct? Is the environment conditions correct? Usage conditions correct? Can I sustain it in the real world? If I can, and if there is a capability for AI to solve the problem, then it becomes a valid problem definition. Alpan, is it correct, my characterization?
Yes, yes.
This is a very difficult thing for people to do naturally, because you will naturally go back to human logic. This is where you need training of your mind. You need to think like this differently.
In other words, if you encounter a problem with the AI model, and something that sounds weird, like why the hell is the model doing this? You have to go back and think about the data. Of course, the other possibility is that the AI scientists have made an error in training it, and there's some bug in training it. But assuming that hasn't happened, then you have to go back and look at what is in the data that has caused this to happen. This is the right question to ask. This is the thinking.
Ayushi?
Yeah. So I think just going back to the pest example, right, where sometimes farmers may take a picture of a white wall or just like a plain surface or something that's not a pest, intentionally in some sense, and the model gives an output. I mean, would it be helpful in problem definition when you're one way to think about, okay, what are the different constraints in which a good video can be taken or a good picture can be taken, and how could someone kind of trick the system or try to misuse it or try to cheat it? Is it valuable to think of that upfront or not?
Yes, it
Or does
is
that complicate it too much?
valuable. It is valuable, but also thinking through what is the best way to solve that problem. The best way may not be to increase the capability of the AI model, because that may involve collecting unrealistically large and diverse amounts of data, but instead to define a protocol with which it can be used. It depends on the situation, right? So we have to do one of two things: either increase capability of the AI model or define a protocol to constrain the use.
Yeah.
And
Yeah.
Alban, to answer to Ayushi, here is how I would have approached this. I would say that this AI model only works when you take a trap with pests on it. I will say upfront, if you take any other surface, a white wall, a green wall, other things, this solution will not work. I will be that, the term is unequivocal, I will be that clear. So you upfront stake your claim of the boundaries in which your solution will work. So if somebody, then you have made a statement directly in the first page of the usage of the application. I will say, अगर आप white surface या कहीं और ले रहे हो तो ये काम नहीं करेगा. ये तभी काम करेगा जब ये environment में ही, and you can bound it. You can say whatever you want, in the correct manner that is meant for appropriate usage of the solution. And I would argue even more. I would say this needs to be part of every single AI solution that we roll out. In other words, the usage characteristics of appropriate usage must be bound set. It must never be kept open. Because you can then set expectations a little better. And if people have a doubt, you can have a neat link of sorts, and you can explain it in simple layman terms, saying that the AI जो है, जो देखता है उसी पे ट्रेन होता है, तो जो नहीं देखता उस पे नहीं होता है, उसमें बहुत कॉस्ट ज़्यादा है. You can explain it in a certain manner, but that is an important communication rather than, kind of keeping it open-ended. It's part of the way we deliver our solutions is what I think we need to do.
Yeah. Yeah, Shekhar, I mean, of course, it'll probably lead into a separate conversation, but in certain solutions, what you just said is quite reasonable and possible, right? In lab setups and those kind of more clinical environments where you have far more trained people, but in slightly, if you look at our anthro problem, or if you look at our pest problem, where it's hard to disseminate this concept. You can disseminate it to like admin level folks. It's hard to disseminate it to the ground, where adoption is needed. And typically that's the challenge. Like with Anthro, I was just thinking, if someone wanted to, instead of going and taking a baby's video, they just, they don't want to go on a visit. They just took a video of, themselves in a mirror or someone just standing, and just wanted to finish the job. Quite possible that we would just accept it, maybe, as a video, as a valid video, and then just project some weight on it. Which, of course, I mean, we can say that, well, that's not, that's not the boundaries of our solution. And, you used it in an incorrect manner, hence you got an incorrect result. But again, it's really hard to kind of, convey that message.
Yeah, agreed, Ayushi. What you're saying is correct. It's how will I put it? This is a problem that, at least in my mind, this is a problem that must be solved in the usage of the application and must be outside the bounds of the AI problem. So the idea of solving this should not and cannot be asking the AI teams to try and detect these patterns. We should restrict the AI within a reasonability of the problem and the environment that they are solving the problem for. And we need to do other things outside the purview of this usage of AI to solve this. And some of this is just broad-based education, even among government personnel, etc. Conversations need to occur so that the educated ecosystem, the literate ecosystem at least, to say, look, when we release AI, don't expect it to work in conditions that are absolutely abnormal. Because it will not. That is not the way it works. So we need to do that. And then operationally, what will start happening is, like all instruments that people use can be misused as well. So this too, as you are citing examples, can be either misused or used outside the context. My going in position, unless somebody tells me dramatically different, is A, not collect more data to solve world problem. B, not even try to tell AI/ML to kind of do anything. They solve the problem within their confines, and we need to have a better communication mechanism, education mechanism. And you're going to get a spurious data here or there. And when we look at it, we'll immediately say, ye hoga hi nahi, ye to ho gaya nahi. Bas, that's it. Because it has to be that answer, because you are not going to be able to solve it. And however difficult it is to hajmo that answer, we have to make it palatable for the counterparty. Because you simply cannot solve it. It is outside the bounds, and the cost, it's just outside the bounds of problem solving, practical problem solving. So we have to sort it outside the AI/ML team, and we should not have them come into this at all at some level. At least that's what I feel, Alpan.
I think it's slightly nuanced. I think some issues should be solved by AI/ML. For example, in the cuff case, we will need to build some kind of model to check whether the person is actually cuffed, right? Not just predict TB from cuff. So things like that, to a limited extent, AI/ML can do. But problems that are just intractable because they require massive amounts of extra data collection to solve, we should just not solve them. Instead, we should specify them as user constraints.
Yeah. Alpan, I know you have a 3:30 meeting. Just one last thought on that is that would it be helpful for us to still think about this during problem definition, all the ways it could be incorrect, and then define, which ones can be solved by AI and which you can't in some sense, and then the solution team should think about it.
I would go further than that. I won't say would it be helpful. It's absolutely necessary to think.
Yeah.
Absolutely necessary. There's no choice. We have to think about it. Sorry, I do have to drop off and I can't go overtime today. But we'll continue. I'll set up 2 sessions for next week as well. Maybe 3 if people are okay with it, but let's see.
I think just for the team to know, Alpan is not available for about a month, starting around May 30 or thereabouts. So he's trying to finish May 20th.
Yeah.
We want to try and finish most of this.
Yeah.
Thanks, Alpan. Thanks, everybody.
Thank you.
Thank you.
Thanks.
Thank you.